We had our relative motion worksheet for homework last night up to question number 6. We're going to take a look at 2 of those questions this morning, starting with number 5, which says the captain of a ship aims his ship with a velocity of 25 meters per second directly north across a river, whose current flows at 8.0 meters per second to the east. The river is 850 meters wide. What's the velocity of the ship? And so on. It asks me a couple of other questions as well. So we remember, as we're tackling the first part of this question at least, that we have 2 types of vectors in these relative motion problems. We have solid line vectors and dotted line vectors. You remember the dotted line vectors are really resultant vectors. So in other words, they result from 2 other vectors. In other words, the dotted line vector results from the solid line vectors. Now, these solid line vectors, if they are what causes the resultant or what contributes to the resultant, those solid line vectors would be things like wind, okay, things like current, okay, things like the way that I head or aim, or the airspeed, the speed of an airplane in still air, or the speed of a boat in still water. Can you tell me what would be my solid line vector or vectors, because there should be 2 of them, in this question? In other words, not what is my actual motion in this question, but what contributes to my actual motion in this question. Tell me one of them. Yep. I'm sorry? Good. Captain is aiming his ship with a velocity of 25 meters per second due north. So we're going to draw that as a solid line vector, 25 meters per second directly north. Make sense? It's not where the ship is going. This is where the captain of the ship is aiming, or this is contributing to where the captain of the ship actually goes. Now, what else do we got for a solid line vector? This river current of 8 meters per second to the east, is that a solid or a dotted line vector? Is this contributing to where the captain of the ship actually goes, or is this actually where the captain of the ship goes? It contributes, so we're going to make that a solid line vector as well. You guys remember the rule, right? When you're drawing a vector diagram, you got to draw the solid lines head to tail or front to back. So we're going to draw this one right here at 8.0 meters per second. And then our resultant vector is going to be drawn right here from start to finish. Now, what have I not put in this diagram? Yeah, Jack? The width. I didn't put the width of the river in this diagram, right? If you're solving a problem involving a vector diagram, you got to be consistent with your units and your quantities. So in this question, I'm using velocities in my vector diagram. Okay, and that's absolutely fine. It's also fine to use displacements, but you've got to be consistent. You can't put a displacement in a vector diagram and a velocity in the same vector diagram. So I stuck with velocities because that's what I have more of. Okay, and solve for the value of r here and solve for the value of theta. When I solve for the value of r, it's the square root of 8 squared plus 25 squared, which gives me a value of 26 meters per second. But that's not enough because velocity is a vector. It requires direction. So we're going to say theta is equal to the inverse tan function of opposite over adjacent. What's the opposite side here? Is it 25 or is it 8? It's 8. Good. So we're going to say the inverse tan of 8 over 25, and that gives me a value of 11 degrees. How would we express that? 11 degrees what of what? Listen, I went north, right? And then I went east, or I went east after I went north, or we're going to just call it east of north, just to shorten it up a little bit. So we're going to say 11 degrees east of north. Okay, how many people got that? 11 degrees east of north, or again, you could have said 79 degrees north of east, right? How many people got it? Okay. Now, B is the tough one. How long does it take the ship to cross the river? This is the one that most people, seeing this for the first time yesterday, were probably not going to get without a little bit of help. Okay, but I wanted to see if you could work through it. How many people could work through it? I suspect a few people probably did. Let's add a little bit more to my picture now here. Now, understand that what I'm drawing now does not form part of my vector diagram, right? The river is not part of the vector diagram, nor is the width of the river part of the vector diagram. I purposely didn't draw that as I was solving question A, because I didn't want to get mixed up between velocities and displacements and think that the 850 was part of my vector diagram. It's not. But it is going to help me with question B. The time that it takes to ship to cross the river. Now, a number of people yesterday, as I was walking around, you guys working on stuff, I noticed we're using this equation, V is equal to delta D over delta T. That's good. That's exactly what I would do to solve this problem as well. It isn't the only way to do this, but it's the way that I would certainly use to do this. Rearrange this, solve for T. T goes up by multiplying, V goes down by dividing. I end up getting T is equal to delta D over V. Now, here's what people did. Here's what a lot of people did, at least. They said the displacement is 850 meters. Good, it's the only displacement that I have. My velocity, 26 meters per second. It was actually 26.2488. What's the problem with that? It's wrong. What's the problem with that? Why can I not say 850 divided by 26.2488? Christine?
You need to do the displacement. That's like the resultant vector.
Good. Yes. If you're going to use that velocity of 26 meters per second at an angle of 11 degrees, then I need to use the velocity, the displacement at an angle of 11 degrees. In other words, when I use this equation, anytime I use this equation, V is equal to delta D over delta T, V and delta D must be in the same direction. Doesn't matter what the direction is, but they've got to be the same. So if I want to use 26, that's fine. That's the diagonal velocity. But I got to use the diagonal displacement, which I don't have. I could find it using the 850 and the angle. I could find the diagonal displacement, but there is a quicker way. As opposed to using 26 and whatever that diagonal displacement is, why don't I just use the 850, which is my vertical displacement. What would I use for my velocity along with that? 25 meters per second. It doesn't matter which displacement I use as long as I use the corresponding velocity along with it. So 850 and 25 works fine. 26 and whatever the value of the displacement is at 11 degrees would be fine. You would end up getting the same answer. In either case, it works out to be 34 seconds. It takes 34 seconds for the shift across the river. Anybody get 36 for that? Or 34 for that, I mean? Okay, a few people? Good. Good. Now, question C. I like this one. I like this one because we've kind of, after having gone through B, we now have kind of a little bit of a hint for question C. How far downstream does the ship end up? What am I looking for here? How far downstream does it end up? Am I looking for a time, a velocity, a displacement? What is it, Jack? No? What were you thinking when you raised your hand there? What were you going to say?
I just thought you were asking, like, if you were looking for R.
Okay, fair enough. What quantity are we looking for? Time, displacement, or velocity? Displacement. How far downstream does the ship end up going? So we're looking for displacement. But we're looking for this displacement, right? The displacement downstream. Now, there's a couple ways of doing this, but again, my suggestion is to do it this way. Once again, V equals delta D over delta T. We're going to rearrange that to solve for delta D. I get V times delta T. V, what am I going to use for V? If I want to find the displacement downstream, then what V am I going to use? I'm going to use the velocity. What is it, 25, 8, or 26? 8. If I want to find the displacement downstream, that's fine. Use the velocity downstream. I just got to be consistent, right? So let's use 8 meters per second. Now, what am I going to use for time? "34 seconds. Now, here's a good question. why do I have to be consistent with my direction for velocity and displacement? I have to make sure that velocity and displacement are in the same direction, and I can't swap over an x and a y velocity or an x and a y displacement, but I can time. Why is it that I can use time, the same time for the ship to cross the river as I do for the ship to go this way, when the displacement and velocity, I couldn't do that? 4 words. Time is a scalar. There is no direction associated with time, right? So it doesn't matter whether I use it to describe going across the river or downstream. Velocity, okay, there's a direction associated with that. It's got to go with displacement. Velocity goes with displacement. But time, there's no direction associated with it at all, so it can be good for x or for y there. All right, when I solve that, 8 times 34, I end up getting 272 meters, which to 2 digits would be 2.7 times 10 to the 2 meters. Anybody get that one? 272? Okay, good. For the few of you that did, that's good. It's a tough question. B and C particularly are really tough questions. But we're better apt to deal with them now, better prepared to deal with them now, right? A big thing is, just remember that if you're using V equals D over T, that's absolutely fine. Just make sure that V and D are in the same direction. Get something. Get something out of it, right? The first one I got T. Okay, great. And the second one, I was able to get the displacement downstream. Okay, now I want to take a look at question number 6. Because the captain of a ship wants to go directly south across a river at 15, but there's a current in the river at 5.0 meters per second to the east. With what velocity, including the direction, because of course velocity is a vector, we need direction, must the captain aim the ship? What do we got here? Captain of the ship wants to go directly south. Let's assume that the captain of the ship is smart enough to go where he or she wants to go. So let's say the captain of the ship goes there, okay, ends up going directly south. Is that my actual motion, or is that contributing to my actual motion? I go south. That's my motion, isn't it? That's my actual motion. That's a dotted line vector. So I'm going to draw my dotted line vector first, directly south at 15 meters per second. Okay, what else I got? There's a current in the river of 5 meters per second to the east. Well, that's certainly a contributing vector or a solid line vector, right? We're going to draw that 5 meters per second to the east. Draw it right here. Does that work? No, it doesn't. The resultant vector, or my dotted line vector, has to be drawn from start to finish, or from the beginning to the end. If I have it drawn like this, there's no way that dotted line vector can be drawn from start to finish, because it's drawn from the finish to something, right? There's no way that I can draw it correctly when I have my 5 meters per second drawn like that. I got a couple of options to do it correctly, but what I would suggest you do when you draw your dotted line vector first is to take your solid line vector that you have and draw it at the end. So draw it down here, such that it's drawn head to head. Why? Well, because that allows me to draw my other solid line vector, my other contributing vector, where I have to aim, my aiming vector. We'll call this A because it's my aiming vector, although you really call it whatever you want. It allows me to draw those two solid line vectors head to tail, and my dotted line vector is drawn from start to finish. Okay? So I want to solve for the value of A, as I'm calling it my aiming vector, and I want to solve for the value of theta as well. A is still the hypotenuse, although it's not the resultant. It's the hypotenuse. So we can solve for A using the same method as we have thus far. Square root of 5 squared plus 15 squared. We do that, we end up getting 16 meters per second, rounded to 2 digits. And theta is equal to the inverse tan function of opposite over adjacent. What's opposite, 15 or 5? 5. And the adjacent side is 15. The inverse tan of 5 over 15, make sure you're in degree mode, is 18 degrees. And we would say this would be west of south. 18 degrees west of south. Look, it looks like, to get to this point, I had to go south, then east, because I have an east vector drawn. But really, to get to this point, I had to go south and west, right? South and west. So it was west after south or west of south. Make sense? Okay, in the end here, look, my 18 degrees here is it measured from the west or is it measured from the south? It's measured from the south, right? Okay? All right, I'd like you to take a look at, let's go with questions 7 and 8 right now. Yeah, let's go 7, 8, and 9 right now. I'll give you a few minutes to work on those, and then we'll take a look at 1 or 2 of those in a few minutes once you've had that chance. Let's have a look at number 8 now. It says the captain of a ship wants to go directly north at a speed of 35 meters per second, but there's a current to the east. The speed of the boat without the current would be 50 meters per second. This is the tricky part of this. It talks about the speed of the boat without the current. What would be the speed of the wind here? Let's draw our vector diagram first, and then we'll worry about labeling it with proper speeds and so on. The captain of the ship wants to go directly north. Is this a solid line vector or dotted line vector? We're going to assume the captain of the ship goes where he or she wants to go, right? So we're going to make that a dotted line vector. That's my actual motion. And we already know what that is, actually. It's 35 meters per second. So we will label that one already, 35 meters per second to the north. It says that there's a current to the east. That's going to be a solid line vector, right? That contributes to my motion. We know that's to the east, so we're going to draw it like this. But where am I going to draw it? Well, my suggestion is, there's 2 places where I can draw it and be correct, but my suggestion would be draw it at the head of my resultant vector. And to do that, I have to draw it like this, because it has to be drawn, let's switch the color though, actually, because it has to be drawn such that the resultant vector is drawn start to finish. Now, what's the value of that? Let's not label that yet, because that's a little bit confusing here right now. And then we've got, what else? Well, we got one more solid line vector here that's going to be right here, right? Okay, so this is my aiming vector, right? This is my aiming vector right here. And then this would be my wind vector right here, right? Make sense? What is this 50 meters per second? The speed of the boat without the current. Is that, where do I label that? A or W? It's A. That's how fast I can aim at. Listen, if there's no wind, I can travel at 50 meters per second. So I'm capable of aiming at 50 meters per second. Now, how fast am I actually going to go? 35 meters per second, right? I'm going to go 35 meters per second because this wind slows me down here. Let's label this as 50. Okay, this is how fast I can aim at, and then let's solve for the wind vector. Now, this is a little bit different than anything else you solved for thus far, because it's not the hypotenuse. We're going to say 50 squared is equal to 35 squared plus W squared. Or W would be equal to the square root of 50 squared minus 35 squared. Does that make sense? Not 50 squared plus 35 squared? Because you're not looking for the hypotenuse here. You're looking for one of the other vectors. For the first time, you're looking for not the resultant vector, and you're looking for not the hypotenuse. So let's go through that one on our calculators just to make sure we can do that as a group here. We're going to say 50 squared minus 35 squared gives me a value of 1275. Let's square root that. And we get a value here of 35.7 meters per second. Or we're going to, what did I say that was? 35.7 meters per second. We're going to round that to 36 meters per second. Is that right? Yeah. Okay. Yeah, that makes sense, actually. I don't have that drawn to scale very well, right? Because seeing that the wind is actually more than my resultant vector, then you can see that it should be drawn a little bit longer. But I didn't know that ahead of time, right? So I I can't zing you marks for drawing that wind vector shorter when you didn't know how long it was when you do your vector diagram. Okay, let's find theta here. Where I have to aim, it's going to be, interesting here. Let's not use tan this time. We were given 35 and given 50. We could use 10 because we got 35 and 36 here now. But I would suggest you use the two values that were given to us, which are the adjacent side and the hypotenuse. This time it's going to be cosine, the inverse cos of adjacent over the hypotenuse. Does that make sense? Makes sense for those of you who did sine, cos, and tan at least? Sine is opposite of hypotenuse, cosine is adjacent of hypotenuse, tan is opposite of adjacent. And when we get to this point to find the angle, we almost always use tan, but we almost always have the opposite and adjacent side given to us. Here we had adjacent and hypotenuse given to us, so we're not going to use tan, we're going to use ca, or cosine is adjacent over hypotenuse. Let's figure out what that value is. Okay, let's hit sine 90 on our calculator. Just make sure here. We get 1, so we're good there. The inverse cosine, be careful you don't automatically use tan. Inverse cosine of 35 over 50 gives me an angle of 46 degrees. And that angle would be 46 degrees west of north. At 46 degrees west of north. Because our angle is measured, look, our angle is measured not from the west, it's measured from the north. So west of north. All right? Anybody get that? Okay, a few people got it. That's good. That's tricky too. Okay, JC just asked a really good question here. Shouldn't I put east here because the wind is going to the east? Just rereading the question here. It doesn't even ask me for direction, right? It asks me for the speed of the wind. The speed of the wind, right? Well, the wind is to the east, but we weren't looking for the velocity of the wind. We were looking for the speed of the wind, right? And if we were looking for the velocity of the wind, which way would the wind be acting? To the east. We're told which way it's acting, right? I labeled here the angle where we're aiming. But we weren't asked for that at all, were we? So I just solved for something that's not incorrect, but I solved for something that I certainly wasn't looking for and certainly didn't need to find. Make sense? So if you're looking for the velocity of the wind, it's 36 meters per second east. If you're looking for the speed of the wind and the direction that I have to aim, 36 meters per second east, and then I have to aim at 46 degrees. Okay? I'm going to leave off that 46 degrees, though, because I wasn't asked for that. Number 9 says the pilot of an airplane wants to fly directly west of Vancouver. All right, this pilot, let's assume that she can fly where she wants to fly. So the actual motion of this airplane is going to be directly west towards Vancouver. We're going to make this a dotted line vector, right? Because this is her actual motion directly west to Vancouver. So let's draw it as a dotted line, just like this. We don't know what the value of that is yet. Okay, there's a wind blowing to the south at 25 meters per second. We know that's a contributing vector. We're going to draw that at the end of my dotted line vector. So my contributing vector or my solid line vector is going to be drawn like this. We know the value of that is 25.0 meters per second. Hey, that's how fast the wind is blowing. The airspeed of the airplane is 100. With what speed does the plane actually travel? Let's label my other solid line vector like this. Hey, such that my solid line vectors are drawn from front to back or from head to tail, and my dotted line vector is drawn from start to finish. Once you've got your diagram drawn, sometimes it's a little bit confusing to draw these diagrams, especially when you're drawing your dotted line vector first or your resultant first. Draw it, and then once you've done it, look at it. Look at it. Have I followed all the rules? Are my solid line vectors drawn from front to back or from head to tail? Yes, they are. Is my dotted line vector, my resultant vector, drawn from start to finish? Yes, it is. So it looks like it's good. Now I got one more number to label here, 100 meters per second airspeed. What is that? Is that going to be the solid or the dotted? Airspeed is how fast the airplane can fly in the absence of wind, right? So that's going to be, what is that? Solid line vector? That's a contributing vector, right? Yeah, that's what I can aim at. I can aim at whatever my airplane will travel with no wind. So I'm going to aim at 100 meters per second. This is going to be 100. And I'm going to look for the value over here, which is, this would be the actual speed of the airplane. I'm going to call that r again, my resultant vector. Right? Back to solving for the resultant. Not the hypotenuse, but I can still solve for the resultant here. Let's solve for, actually we're just looking for the value of the speed, which is fine because our actual speed is going to be directly west, right? So it doesn't really make sense to find direction when we know what the direction is already. Let's just find the value of r. All right, we know that r squared plus 25 squared equals 100 squared, or a squared plus b squared equals c squared. We're going to solve for r. It's the square root of 100 squared minus 25 squared. And when we do that, let's figure that out as a group here. Let's say 100 squared minus 25 squared equals 9375. Let's square root that. And we end up getting 96.8, or we're going to round that to 97 meters per second. So the airplane can head at 100 meters per second, but because of this wind, the airplane has actually slowed down a little bit. Sometimes we see that the wind actually causes it to speed up a little bit, but sometimes we see it actually causes it to slow down a little bit depending upon directions. And that makes sense, right? It depends on which way the direction of the wind is, whether it causes us to speed up or slow down. Okay?